video is going to go over some of the concepts that you struggled with on the Unit 2 homework. In section 4.4, there we have an example. It says, assume that a company hires employees on the different business days of the week, Monday through Friday, with equal likelihood. Part A says, if two different employees are randomly selected, what is the probability that they were both hired on a Thursday? So the probability of one of them being hired on a Thursday is 1 out of 5. They were hired on Thursday, and there were 5 possible days, Monday, Tuesday, Wednesday, Thursday, Friday, that they could be hired. Both is another way to think of and with and, we need to multiply. So the probability that the first one was hired on Thursday was 1/5. The probability that the second person was also hired on Thursday, or actually just that second person was hired on Thursday, was 1/5. When I multiply them both, I find that the probability of them both being hired on Thursday was 1 out of 25. Now part B is where it gets a little tricky. If two different employees are randomly selected, what is the probability that they were both hired on the same day of the week? So it's most people's first inclination to just go 1/5. We just did that. But what they're really saying is, what's the probability that they're both hired on Monday? Or they're both hired on Tuesday? Or they're both hired on Wednesday? Or they're both hired on Thursday? Or they're both hired on Friday? Any of those options will work. So the probability that they're both hired on Monday is 1/5 times 1/5. The probability that they're both hired on Tuesday is the same thing, as is Wednesday, Thursday, and Friday. Now for this one, we have or separating each of them. And or is our keyword for addition. So what I'm really going to need to do is multiply each of these to get out that 1/25, and then add all of them up. When I do that, I end up with 5 over 25, which really reduces to 1/5. So it's more likely that I'd have two people hired on the same day, rather than saying they have to be hired on Thursday. On part C, they ask me, what is the probability that 5 people in the same department were all hired on the same day of the week? Is such an event unlikely? So if I look at this all hired on the same day of the week, it's similar to part B. So I'm going to need to think about my 1/5 times my 1/5, but this time there were 5 people, so I need times 1/5 times 1/5 times 1/5. Another way to write that to make your calculations a little bit easier is 1/5 to the power of 5. Now that would only address one day of the week. I also need to add in the same thing for Tuesday and for Wednesday, also for Thursday. I also need to worry about Friday. If I do that math, I end up with 1 over 625. If we look at another one from section 4.4, it says a tire company produced a batch of 6,800 tires that includes exactly 290 that are defective. For part A, it says if 4 tires are randomly selected for installation on a car, what is the probability that they are all good? So the first thing we need to do is figure out the probability that they are good, because they only tell us about defective. So if we take that 6,800 and subtract 290, that tells us that 6,510 tires are good from that batch. So if I'm thinking about the first tire they draw, it'll be 6,510 out of 6,800. But then for the second tire, they're not putting that one back in. So there's only 6,509 good tires left. And there's only 6,000 799 tires total. The same thing happens where my numerator needs to go down by 1 and my denominator needs to go down by 1 for my third tire, and then I repeat that process for my fourth tire because I'm not replacing the tires that I'm taking out. When you put that in your calculator, you get 0.83998444127. And if we use that rule where we round to 3 significant digits, I'd say this probability is about 8.40, because that 9 tells me to round that other 9 up. Now, if we look at part B, we're looking at that same situation, but we're going to look at 100 tires. So in theory, we could do what we did above in part A and just do it 100 times, but that's a cumbersome calculation. So if you guys remember, we learned that rule that if our sample size is less than 5% of our population, we can assume they're independent. So if we find what 5% of our population is, that 0.05 times 6,800, we find that 5% of our population is 340. So our sample size of 100 is less than that 340. So we can make the assumption that they're independent even though they're not, because it's not going to affect our calculations in a big enough way, and we can avoid those cumbersome calculations. So that means I'm really going to take my 6,510 over 6,800 and assume that that's the thing I'm going to multiply 100 times for every tire I'm picking. And instead of multiplying it out 100 times, I'm going to raise it to the 100th power. If I do that, I get 0.01279999298. And same thing, I'm going to round to those 3 significant digits, so I'll have 0.0128 as that probability. If we look at part C on that homework, it was multiple choice. They said, should this outlet plan to deal with defective tires returned by consumers? So if we look back at part B to help with our decision, if we drew 100 tires out, there's about a 1% probability that they're all good. So that's an issue. So that means they should have a plan because there is a very small chance that all of them are good. So I would pick that option. 4.4 was causing a lot of issues, so we're also going to look at this one. Find the probability of correctly answering the first 5 questions on a multiple choice test if random guesses are made and each question has 3 possible answers. So the first thing we need to do is figure out that denominator of our probability. How many different things could we get? So to do that, we're going to use our fundamental counting principle. If you think about question 1, there were 3 possible answers. Question 2 also had 3 possible answers. Question 3 had 3 possible answers. Question 4 had 3 possible answers. And question 5 had 3 possible answers. Right? I'm not doing a combination or permutation because I'm not choosing how many questions to answer. I'm guessing one of my answers, or actually all of my answers. So if I do that, that's the same thing as 3 to the 5th power, and that's going to give me 243. So that's telling me there's 243 different ways I could answer those 5 questions. There's only one way to get all of them right, if I get all of them right. So the probability of getting all of them right on guesses is 1 over 243. If I write that in decimal form, I get this big long number, just like we've talked about before. I round to 3 significant digits. And I'd have this very small probability that I'd get it right by guessing. Now if I look at this next one, it says the manufacturing process has an 80% yield, meaning that 80% of the products are acceptable and 20% of them are defective. If 3 of the products are randomly selected, find the probability that all of them are acceptable. So that's like saying the first one's acceptable, and the second one's acceptable, and the third one's acceptable. That and is telling us to multiply. The probability that one of them is acceptable is 80%, or 0.8. So I'm going to do 0.8 times 0.8 times 0.8. That gives me 0.512 as my probability. If I look at another one from section 4.4, it says an IRS auditor randomly selects 3 tax returns from 48 returns, of which 6 contain errors. Find the probability that she selects none of those containing errors. And we're going to round to 4 decimal places. So if we look at it, there were 48 total returns. 6 of them had errors. We want the ones that do not contain errors. So just like we did with the tires, I'm going to take the total and subtract out the ones that have errors. So that means there's 42 with no errors. So if I'm thinking about the probability that she selects none that have those errors, well, the probability the first time is 42 out of 48. But then the second time, there's only 41 left without errors and only 47 total tax returns. Same thing when I do 40 over 46, because it's none of those containing errors, they both go down. When I do that in round, I end up with 0.6228. If we look at one from section 4.5, sometimes these conditional probabilities can be a little difficult. It says the table below shows the soft drink preferences of people in 3 age groups. If one of the 255 subjects is randomly selected, find the probability that the person is over 40 years of age, given that they drink cola. Express your answer as a simplified fraction. So if we think about writing this using our probability notation, right, we want the probability that they're over 40 given that they drink cola. So that means when I look up at the table, I need to focus in on only that cola column, because that's what's given. Then I look at the over 40 in that column. The over 40 in that column is 20. So my numerator is 20. My denominator is all of the people in the cola column, not the overall. So when I do my 40 plus 35 plus 20, that gives me 95. So I have a fraction 20 over 95, but it's not simplified. I can divide both of these by 5, so my simplified fraction is 4 out of 19. If I look at section 5.2, this was where we were talking about our binomial distribution. Or no, I'm sorry, this was just our plain old probability distributions. It says, in a states pick 3 lottery game, you pay $1.28 to select a sequence of 3 digits from 0 to 9, such as 100. Right, our 3 digits are 1, 0, 0. If you select the same sequence of 3 digits that are drawn, you win and collect $468.52. For part A, to figure out how many different selections are possible, we use our fundamental counting principle. There's 10 options for our first number, 10 options for our second number, 10 options for our third number. So there's 1,000 possible options. There's only one that wins. So our probability is 1 over 1,000, or 1/1000th. If we think about our net profit, it's what we collect minus what we bet. So that would be our 468.52 minus what we bet, our $1.28, which gives us a net profit of 467.24. To find our expected value, remember that's the same thing as the mean, we add up or sum all of our x's times our p of x's. Right, that's what our expected value equals. So when we did one like this in class and we set up a table, I said that it was easy to think of it in terms of what we get when we win and what we get when we lose. Right? When we win our X, we actually make $467.24. When we lose, so it's negative $1.28. We just found the probability of winning was 1/1000th. That means the probability of losing has to be 1 minus 1/1000th, or 0.999. When we multiply straight across, because that's what it tells us to do, we'll end up with 0.46724 and negative 1.27872. When I add these up, because that sigma tells me to add, I end up with negative 0.081148. But we're talking about money, so they told us to round to the nearest cent. So we're expected to lose 81 cents every time we play the game. If we look at part E, knowing that expected value helps us figure out what's going on. Part E tells us if you bet $1.28 in a certain state's pick 4 game, the expected value is negative 0.81. That's the same expected value we just had. So they're saying which one's better. And in this case, neither one is better. Our expected value is the same. We're going to lose about the same amount no matter which game we play. If we look at section 5.3, I tried to pick a couple problems that looked tough because most of you had not gotten to this homework yet. So if we look at this one, it says a TV show, Lindsay and Tobias, recently had a share of 15, meaning that among the TV sets in use, 15% were tuned to that show. Assume that an advertiser wants to verify that 15% share value by conducting its own survey, and a pilot survey begins with 25 households having TV sets in use at the time of a Lindsay and Tobias broadcast. Part A tells us to find the probability that none of the households are tuned to Lindsay and Tobias. So this is a binomial probability distribution. There's only two options. You're tuned in or you're not. They give us a probability of each success, and those successes are assumed to be independent. So in this case, our N is 25 because we're looking at the 25 households. The probability of success, saying that they are tuned into this TV show, is 0.15. Our probability of failure is 1 minus that 0.15, so that 0.85. And in this case, because they're asking us none of the households, our X is going to equal 0. So we're going to go to our calculators and do our binom PDF option. Remember, you get to that by second varies. And we're going to put in 25, 0.15, 0. And that gives us this probability. And we're going to round it to 3 significant digits. So we'll round it to 0.0172. We look at part B, it says find the probability that at least one household is tuned to Lindsay and Tobias. So this combines something we learned back in chapter 4 with our complement. At least one is the complement or the opposite of 0. So they're really just saying not 0. So we can use our answer from part A, because if we want the probability that it's not 0, we just do 1 minus the probability that it is 0. And that'll give us 0.9828. If we look at part C, it says find the probability that at most one household is tuned to Lindsay and Tobias. So that means that 0 households or 1 household is okay. So we want to find the probability of 0 and add the probability of 1. So we already know our probability of 0. It was that 0.0172. We need to find that probability of 1. So we go use our calculator to find our binomial PDF calculation when our N is 25 Our probability of success is 0.15. And this time our x is 1 because we want that one household. When we do that, we get about 0.0759. And when we add these up to get our final answer for this question, we get that the probability is about 0.931. If we look at part D, it says if at most one household is tuned to Lindsay and Tobias, does it appear that the 15% share value is wrong? Why or why not? So with this, we need to think back to one of those definitions of unusually high and unusually low. And we had that if X successes among N trials is unusually low or unusually high, so we'll say unusual, if, in this case it's low because we're looking at 0 or 1, something below, if P of X or fewer, that's the definition we're looking at, is less than or equal to 0.05. So if we look back up, we had 0.09. It's not below that. So our answer would be no, it does not appear to be wrong. If we look at section 5.4, same thing, I just tried to pick one that looked difficult because most of you had not reached here yet. It says a headline in a certain newspaper states that most stay at first job less than 2 years. That headline is based on an online poll of 410 college graduates. Among those polled, 87% stayed at their first full-time job less than 2 years. Assuming that 50% is the true percentage of graduates who stay at their first job less than 2 years, find the mean and standard deviation of the numbers of such graduates in randomly selected groups of 410 graduates. So for this part A, I'm essentially ignoring that 87%, and I'm going to use 50% instead. Now this is a binomial probability distribution because there's only two ways, yes or no, right? Two options there, that they stayed at their job or they didn't. It's independent because at the very least it's a small group, and we can go from there. So our definition of our mean when we know it's a binomial distribution is n times p. Our n is the 410, the survey size. We're assuming the probability to be 50%, which gives us 205. Our standard deviation is our square root of n times p times q. So it would be the square root of 410 times our probability of success times our probability of failure, which are both 50%. And that gives us 10.1242287. So we round to 10.1, one digit past it. Remember, we want to try to include units here. So if we look at it, it was a percentage of graduates. So we would say 205 graduates, 10.1 graduates. If we look at part B, they tell us assuming that the 50% rate in part A is correct, find the range of usual values. We do that usual value with mu plus 2 times the standard deviation and mu minus 2 times the standard deviation. So we'll have 205 plus 2 times 10.1, which gives us 225.2. And we'll have 205 minus 2 times 10.1, which gives us 184.8. For part C, they tell us find the actual. So they're telling us to look back up at that original data. Number of surveyed graduates who stayed at their first job less than 2 years. And use the range of values from part B to determine whether it's unusual and does it suggest that the headline is justified or not justified. So if we look back up at the actual, it wasn't 50%. It was 87%. So I'll do 0.87 times 410. If I do that, that gives me 356.7. If we look at our usual and unusual range, this is definitely unusual because it's above that 225.2. So our answer would be yes, it is justified. If we look at part D, they tell us the statement alumni who opted in to receive communications from the website were invited to participate in the online poll, and 410 of them completed the survey. It was given as part of the description of the survey methods used. What does this suggest about the results? If you think back to what we learned about back in Unit 1, this is a voluntary response sample. Right? They chose to opt in. Because of that, it's flawed. We don't want to generalize this.